Good morning, GLA middle schoolers. Today's date is going to be Tuesday, May 5th of 2020. I have to say I've been very impressed with how many of you folks have gone back since I gave the little video lesson on how to look at your grades yesterday and started doing some old assignments. I saw Serenity completing a bunch of old assignments. I saw Shavella, I saw Kai, and a few other people whose names I can't even think of right now. I'm very impressed with you guys taking responsibility for your grades and looking back through all of that information. If you, whoever you are listening to this video right now, have not yet gone and looked through your assignments that I show you how to do on yesterday's video, I would say you should go and do that now and make up any assignments that you have missing before you do today's video lesson. Because we're going to be picking up on where we left off from last Thursday and kind of building onto that new knowledge, and I want it to make sense. Alright, so getting to today's new content, we'll be talking today about the idea of conservation of mass. To start us off, I want to kind of refresh though, because it's been like 4 days now, I think since Thursday that we had a real science lesson. So I want to kind of remind you guys what it was, the stuff that we were talking about and what we were learning back on Thursday. First of all, you know that in our unit right now in chemistry, this thing we keep on saying is that anything that has weight and takes up space is matter. It's a word we're using a whole bunch. Stuff, anything that you can touch that's around you in the world is matter. The only things that aren't matter are things like dreams or thoughts or visions or stuff that doesn't actually, you can't touch, doesn't have weight or just take up space or anything. Second of all, matter has properties such as color and reflectivity and solubility and so on. We've learned about a whole bunch of different properties like that. And third of all, that matter can change. Specifically, matter can go through two different types of changes, and that's what we were talking about during our most recent lesson on Thursday. This is a picture of our slides from Thursday, and that was in the video. We learned that those two types of changes that matter can go through are physical changes and chemical changes. And I had you guys draw a T-chart and write down a whole bunch of stuff about physical changes and a whole bunch of stuff about chemical changes. So, right now I want to just try to kind of quiz you and see how much you remember from that. So here's classwork question number 1. It is going to be to simply list anything that you can remember about the differences between a physical change and a chemical change. Now remember, these are graded for effort, not accuracy, so I want you to sincerely think through your head, like, okay, what are some things that I can really remember about the differences between these two things without using your notes, without looking back at the video. It's just graded for effort. So if you really can't remember anything, say so. Maybe I can jog your memory, though, to say we talked about one of these changes has to do with creating a new substance, and one of them doesn't. Maybe ask yourself, can each of these changes be undone? Are there maybe some signs that will tell you whether one of these changes has occurred? Go ahead and pause the video and answer classwork question 1 now. Alright, I'm assuming that you have now answered classwork question number 1 because we're going to talk about the differences right here. That will make it way too easy. To recap, there are the two types of changes. A physical change is the most important thing is that it's one where no new substances are created. You don't get any new kinds of stuff going on. The particles that were there are still the particles that you have afterwards. A physical change can be undone. You can undo it. And it does not meet any of the 6 signs of a chemical change. We talked about those 6 signs, things like smelling something or light or heat being created. Physical changes don't meet those 6 signs. And if you're like, that's all sounds too abstract or weird, Mr. Manta, what are you talking about? Some examples of physical changes are things like melting, freezing, boiling, or making a solution. So a few people had said in the comments, they're like, if you had a bowl of ice cream and it melted and you had melted ice cream, what kind of change is that? Well, that would be a physical change because melting is always a physical change. But you're not creating any new substances. You just have ice cream, but it's in melted form now. You can undo it if you refreeze your ice cream, and it doesn't meet any of the 6 signs of a chemical change. You don't create any new smells or heat or light. There's no fizzing or anything that tells you that a chemical change is going on. Now, on the other hand, we do have chemical changes. These are different from physical changes, most importantly because a new substance is being created when you have a chemical change. They generally you can't undo them, they cannot be undone. So once a chemical change has happened, you've created a new substance and it's probably going to stay that way. And they will always meet some of the 6 signs of a chemical change. Things like producing light or heat or fizzing because a new gas is being made, something like that. And again, I'm going to give you some examples. Things like anytime you burn a match, you're causing a chemical change. When we bake a cake, we said that's an example of a chemical change. Or if you do an elephant toothpaste reaction, then you are also creating a chemical change, or making this new thing called elephant toothpaste that didn't exist before. All right. The last part that we also mentioned on Thursday that I want to remind you of, that was kind of simple, so hopefully this won't confuse folks too much, is some vocabulary that has to do with our chemical changes. We learned that anytime we have a chemical change, you start out with this stuff that you call the reactants. Once you mix something or start your chemical change somehow, you go through a chemical reaction, and that is the process of your reactants, well, reacting and creating something new, and you end up with this new thing that you've created, which we call the products. Anytime you have a chemical change, you have kind of these three parts: the reactants, the chemical reaction, and then the products. The stuff you start with, the change itself, and the stuff you end up with. So, for example, whenever we bake a cake, you start out with your reactants. In this case, your reactants are flour and sugar and butter and milk and all that stuff mixed together inside of a baking tin. You go through the chemical reaction, which in this case is baking the cake, and you end up with your products, which in this case is a fully baked cake. And of course, you will see some of the 6 signs that a chemical change has happened. You have changes in properties, you've created smells, gases, all that kinds of stuff. All right, taking all of that information, now it is finally time for today's Do Now. So go ahead, if you don't already have your notebooks out, make sure you go and get it out, because yes, you need to answer these 5 questions in your notebooks right now. Question 5 is my favorite one because it requires you to think all the way back to the stuff we learned in Unit 5 when we were still in class together. All right, go ahead and pause the video, answer these 5 Do Now questions in your notebook now. Alright, I'm now assuming that you have done that. We are moving right on to show the answers. Number 1. Which type of change results in a new substance being created? That is always going to be a chemical change. Number 2. Which type of change can be undone? That's going to be a physical change, something like melting ice cream, where you can undo it by refreezing the ice cream. For number 3, Susan lights a birthday candle. As the candle burns, it combines wax and oxygen to create smoke. In this situation, what are the reactants and what are the products? Well, it said pretty clearly that she's combining wax and oxygen to create smoke. That's what burning does. It combines something like wax or wood, some kind of fuel, with oxygen that's in the air, and it creates the smoke out of it. The fire is just kind of like the byproduct, but that's too complicated for now. But point being, because you're starting out with wax and oxygen, those are your reactants. Because you're creating smoke, your product is smoke. So your reactants are wax and oxygen, and your product is smoke. Number 4, what type of change is happening when Susan burns the birthday candle? Well, that's going to be a chemical change. So like we said, she's creating smoke here. She's creating a new type of matter from something else that she started with. And number 4, think back to Unit 5 on energy. We learned about the law of conservation of energy, which says that energy can never, I'm very impressed with those of you who remember this one, be created or destroyed. We said you can transfer energy, you can convert it, but you never have energy being created anew, and you never have energy that just disappears or gets destroyed. The amount of energy in the world and a system is always the same. It's just being transferred or converted into different types and different objects. Now, knowing this about the law of conservation of energy, it's going to make today's lesson a whole lot easier for you, because today's new idea is an idea called the law of conservation of mass. And if you know about the law of conservation of energy, that energy can never be created or destroyed, well, yes, that's going to help you quite a lot, because it's a very similar idea, this law of conservation of mass. To learn what it is, we are going to go to Crash Course as always. But if I need to remind you, on our last lesson, all the way back on Thursday, we actually cut off right in the middle of our Crash Course video, and I don't want to confuse you guys. So just to remind you of where it was that we left off in Crash Course halfway through, what was going on was that our host Sabrina, who's that woman who talks to us on Crash Course, left a glass of water out for a while, and noticed, when she came back to it, that it was less full than it used to be. So she left a glass of water, maybe like this one, out on a counter or something, and then 3 hours later she came back to it, and you notice beforehand she had this water that filled all the way up to here. Now she has less water. The glass is less full. So she's wondering what happened to that water, and specifically she wanted to know what happened to the missing water. Does matter ever just disappear? Does it ever just go away, get destroyed, just pop out of existence entirely? Well, let's find out. I'll hop over to Crash Course. It will pick up with the stuff from last week, and then it will start going into the new material. Listen closely.
In a chemical reaction. The reactants are things that react. They're what get changed during the chemical reaction.
Reviewing
and the
our
new substance
reactants
that's
and
made,
products.
that's the product. In our chemical change, the ingredients of the cake contained the reactants, and the cake was one of the products. So, matter can change.
And
But
the
what
new
matter
material.
can't do is just appear or vanish. And since all matter has mass, this means that mass can't appear or vanish either. Scientists have been experimenting with this idea for hundreds of years. Lots of experiments have provided evidence of what we call the conservation of mass. The conservation of mass is the scientific rule that says the mass, or the amount of matter in an object, is never made and never lost. So, what about the water from my glass? Well, it didn't just disappear. As the water evaporated, its molecules became mixed in with the air molecules, so it went through a physical change. It's still there, but we just can't see it anymore. Let's try making a solution like we did on our picnic. Say you mix 5 grams of sugar into 10 grams of water. Remember that grams are the unit of mass. Then you stir your mixture until the sugar looks like it disappears. We started with 15 grams of materials, the 5 grams of sugar and the 10 grams of water. And when you weigh the new solution, sure enough, you'll get 15 grams. There was no change in the amount of mass that you have, even though we don't see the sugar anymore. The sugar didn't vanish, it just went through a physical change. It dissolved. But if you could gather up all the dissolved parts of sugar and weigh them together, they'd still equal the 5 grams that you put in. And we'd find the same thing if we measured the mass of the water in my glass. If we measured the mass of water that's left in my half-full glass, and we were also able to catch all of the water molecules that escaped into the air and weighed them, together they would weigh the same amount as the water in my glass when it was full. Conservation of mass. So, the scientific rule called the conservation of mass tells us that matter is never made or lost. It just changes. We showed this by creating physical changes, in which matter just changes its form. In this case, whole sugar into dissolved sugar. The conservation of mass also applies in chemical changes too, in which a new substance is made. But that's a topic for another day. See you next time!
Alright, ladies and gents, there you have it, the law of conservation of mass. Surprise, surprise, not all that different from the law of conservation of energy. So, let's bring it back and recap what it is that we just learned from Crash Course. Today really has just one big, bold, key point. It is this. If you're going to write anything down in your notebooks, which, by the way, hey, I mean, you should be writing a lot of things down in your notebooks, but if you're going to write just one thing down today, write down this. The law of conservation of mass says that mass can never be created or destroyed. Sounds familiar? It's the exact same idea as the law of conservation of energy. Just like energy, mass can change forms or go somewhere else, but you can never just destroy old mass or create new mass. It can never be created or destroyed. It never just disappears. It never just suddenly comes into existence. It never just suddenly goes out of existence. The amount of mass in a system, in the world, in the universe, is always the same. And by the way, you might be a little bit confused because I'm going to be kind of back and forth using the words matter and mass interchangeably today. Sometimes I'll say matter and sometimes I'll say mass. They're basically the same thing. Like, really proper scientists would be mad at me for saying that. But at least in this case, you can say either one. You could say that mass can never be created or destroyed. You can say that matter can never be created or destroyed. It means the same idea, at least in this situation. Now, they gave us a couple examples of that in Crash Course. This was the first one. That's pretty clear. It makes sense. If you take some sugar and you combine it and stir it into some water, you end up with this mixture, this solution that we call sugar water, which are those two things combined. And if you do this on a scale, like they did in the video, and you weighed that you had exactly 5 grams of sugar, and you weighed out exactly 10 grams of water, and then you weighed it at the end, you would find that you had 15 grams of sugar water. Because even though you can't, like in this sugar water at the very end, you can't see all the little grains of sugar that are in there. They're all still in there. It's just that the particles dissolve. They all separated and spread out into the water, so they're too small for you to see now. But you still have 5 grams of sugar and 10 grams of water in there, and that adds up to 15 grams of sugar and water together. That makes some sense. That's pretty clear to me. And so I'm going to follow that up with a classwork question, and that is this. Stephen mixes 30 grams of lemonade powder into 200 grams of water to make lemonade. How much mass will the lemonade have? And how do you know? Make sure you answer both parts of that question for classwork question 2. Pause the video and answer that now. Dun, dun, dun. All right, I am now assuming that you've done that. We're unpausing and moving right along. Now, to follow up that first example, they also gave a second example that's a little bit more difficult, so I want to spend a minute on it right here. And that is this example of water evaporating into the air. What Sabrina is saying is that you can have a glass of water, and you could weigh it on a scale, and it would maybe weigh like 50 grams of water. And then if you wait some time, like 3 hours, and you come back to that glass of water, it will look like there's a lot less water. And if you weigh it, like, so up here, right, you have the water level all the way up here, and down here you have less water. And even if you put it on a scale, it would actually weigh less. You might have 30 grams of water at the end, where you had 50 grams at the start. And those two numbers are clearly very different. So if you saw this situation happen and you saw all that water apparently disappear, you'd be thinking, oh my God, did the 20 grams of water just disappear? You'd be thinking, did I just find a violation of the law of conservation of mass? And the answer is no, you did not. Because the law of conservation of mass says mass can never be created or destroyed. Well, if the water didn't just disappear, if it wasn't just destroyed, well then where did it go? What happened to it? What actually happened to it is that it evaporated. Now, we learned about evaporation all the way back, like in Unit 3 or 2, I think, when we were talking about the water cycle, right? The water cycle where water kind of continues to go from one place to another into the mountains and the oceans and all that kind of stuff. Evaporation was this step of the water cycle where water in the ocean or lakes or rivers evaporates and it goes up into the air. It especially evaporates when it's getting a lot of sunshine. But basically, tiny little particles of liquid water evaporate out and go up into the air, and eventually they condense and they form what is going to be clouds up here. If you remember some of those terms, I know it's been a long time, but the basic idea is that anytime you have water, little particles of it very slowly are evaporating up into the air, becoming water vapor instead of liquid water is what we call it. And that's what happened to the water, to the water in these glasses. That's why you have more water here and less water down here, because little individual particles are constantly evaporating out into the air. They're not being destroyed. They're not vanishing. They're evaporating. Well, how could you know that that's where they're... How do you know for sure that they aren't actually being destroyed? Well, here's how scientists figured that out. It's a really interesting little experiment. If you take your glass of water to start off with, like we had before, but you put it inside of a glass box that is totally closed off, it's totally sealed off, nothing can escape out of it, and you weigh the whole box with the glass of water in it, you might start off with a glass box that altogether, the box and the glass of water and the air inside of it and the water weigh something like 100 grams. You could weigh that whole glass box and everything inside of it on a scale together and get its mass. We'll say in this example 100 grams. Now, if you waited for 3 hours, you would again see that the water level in the water would go down. You would have less liquid water than you started with before because the water is evaporating, right? But in this case, since the whole thing is trapped by this glass box, even when the water is evaporating, it's still staying inside of this glass box. And so you'd have little particles of water floating around inside the box that weren't there before. And if you took the whole box and you put it on a scale and you weighed it again, then it would still weigh 100 grams. It would still have the exact same mass that you weighed earlier because all that water that previously was kind of escaping or evaporating is now trapped inside of this box. The point is that even when you didn't have the box, the water wasn't being destroyed, it was just kind of evaporating or escaping or going somewhere else. Because water is never, ever, ever being destroyed. Because matter is never being destroyed. It's never being created. Because that's what the law of conservation of mass says. The box is just there to trap that evaporating water so that you can still weigh it even after it evaporates. To conclude for today, the main point that you need to take away from this is that matter or mass, you can say either one, can never be created or destroyed. The law of conservation of mass says so. And in case you were wondering, because we've talked about two different types of changes in chemistry, this is true for physical changes and it's true for chemical changes, but we'll probably talk more about chemical changes in the next few lessons. But since it says it can never be created or destroyed, hey, then you know that's true for physical changes, it's true for chemical changes, for any kind of change ever, because it can never be created or destroyed. Alright, knowing that, we're going to move on to today's independent practice. So open that notebook opening and get your pencils ready, and go ahead and answer these 8 questions. Pause the video and complete today's independent practice now. Alright, I'm now assuming you've done that. You're unpausing the video because I'm going to show you the answers. For number 1, there are 2 kinds of change that can happen in chemistry, a physical change and a chemical change. Number 2, the most important thing about a chemical change is that a new substance is created. That's really the thing that defines a chemical change, that makes it the most different from a physical change. Number 3, the law of conservation of energy says that energy can never be created or destroyed. And number 4, the law of conservation of mass says that mass can never be created or destroyed. They're the same idea, just for mass versus energy. Number 5, Donovan eats a cheeseburger. Was the matter that makes up the cheeseburger destroyed? No. Your answer should have been no, because even though we didn't talk about cheeseburgers at all during this lesson, you know that matter is never created or destroyed. In this case, he ate the cheeseburger, and it just went inside of him. He's digesting it now. He's going to use it to grow his muscles big and strong, but the matter's not going away. Number 6, Linda grows a sunflower in her garden. Was the matter that makes up the sunflower created out of nothing? The answer is no. Even though we didn't talk about sunflowers, you should know that because matter is never created. You can never just create new matter. Instead, what's happening is that the sunflower is taking in energy from the sun and carbon dioxide from the atmosphere and nutrients from the soil and water from the soil, and it's assembling all of that matter to grow, to make more of itself, basically. Plants, if you really want to think about it and get weird with it, plants like sunflowers are they're like little machines for assembling water and carbon dioxide into more plant. But they can never, when something's growing, it's not like making new matter out of nothing. It's assembling nutrients and vitamins and stuff into more of itself. Number 7, Derek dissolves a teaspoon of salt in a glass of water. Was the salt destroyed? Well, if you've been paying attention, you should know that no, it was not, because matter is never destroyed. And number 8, is the law of conservation of mass true for physical changes? Is it true for chemical changes? Your answer there should be yes and yes. It is always true. It doesn't matter what kind of change you're talking about. As always, go ahead and finish off today by starring the questions you got right, fixing those answers you got wrong, and telling me in today's classwork form which ones you got right off the bat. And that will bring us to today's exit ticket. Go ahead and start knocking out that exit ticket. People have been doing really well with those lately. And yes, 6th grade, you know you have a progress report coming up. By the way, 6th grade, you need to have all assignments into me by the end of the day tomorrow, Wednesday, so that I can do your grade reports. Any assignments you do by the end of the day tomorrow will count towards the grade that you're, like the progress report you're getting on Friday. So if you're going to make anything up, make it up like today or tomorrow morning, super soon. Don't wait for it. Last thing to mention is today's cool thing. A lot of people liked the last today's cool thing I did was about Morse code, and I showed you guys how to use a Morse code translator, and that's like a super secret code language that spies invented a long time ago. Well, I want to show you another cool language. This one is called binary. And binary is the language that computers and machines actually speak. In binary, there are only 2 letters. You know, like in the English, in our alphabet, we have 26 letters, A, B, C, D, E, all that kind of stuff. In binary, there's only 2 letters. There's only 0 and 1. But even though they only have those 2 letters, they can say anything that you would ever want to say. So, for example, this is how you would say in binary. I believe the sentence is science rules. I'd have to look back at it again. But I'll put a link, an optional link, just to play around with, to a binary translator if you want to figure out how to write some secret code in binary as well. Maybe you can use it to speak to a computer sometime. All right, that is all we got for today, folks. Thank you for your attention and your hard work as always, and I will talk to you tomorrow.